So for the lecture question, this is kind of the standard cliched inheritance example. I'll give it to you as a lecture question because I don't like lecturing this one, just because it's what everyone uses to introduce inheritance. But create an animal class and then extend that class into two other classes named cat and dog that will override some of that behavior. And we'll talk about how we're going to do this and what that means. For the quiz, a lot of you are asking about the quiz, understandably. So a quiz question is going to look something like this. If you can understand this question, then you should be solid with everything on the quiz. This will be the harder questions on the quiz. The other ones will be, here's a class. Here's some code that instantiates this class and calls some of its methods. What's the state of the object at the end? I'm going to ask you questions like that. But this will encompass that as well. So given this, obviously this is the example we saw in the slides. Given this code, when execution is at that green arrow, draw the stack and the heap. So I want to know that you can trace through a program and keep track of every variable that's going on the stack, every variable that's going on the heap, and how those references are actually stored in memory in the stack and the heap. If you can do this, if you're good on this without having to look back at the slides, you're going to be solid. For this one, obviously you had the answer in the slides from last week, so you can go back and look at how that was, so you can get practice with that quiz. Yep.
When we're done with the statements and for loops and things of that nature, do we just toss them out? Or like, how do you...
Yeah, so the question is when we're done with if statements or for loops. So I'm asking about the state of memory exactly at this point. So for example, the if-else statements with if bird.inDanger creates this variable named action, or this value named action. By the time you get to the execution where that green arrow is, that block of code is ended and those variables are no longer on the stack. So you would not draw those, you wouldn't cross them out or anything. If you want to sketch out how the program progresses on the side of your quiz, draw it out to help you out, that's fine. But when you give your final answer, you shouldn't have those values on the stack anymore. Because at the green arrow, that value action that was created in that if statement doesn't exist anymore. So it's not on the stack, so you shouldn't draw it in your answer.
So then how do you represent it when it's over with?
You just wouldn't, it's not on, at that green arrow, it's not on the stack at all. You just wouldn't draw it at all. Doesn't exist. And any function calls, so the print line, box.inDanger, bird.inDanger, and or at least one bird.inDanger stack frames that were put on the stack, all those stack frames are gone by the time we get that green arrow too. So actually, for this question, we wouldn't have any stack frames on the stack except for the main method. So you wouldn't even draw those at all. You wouldn't draw those stack frames that were created and then destroyed. I'll give you, and I guarantee I'll give you one question like this where you're going to have multiple objects on the stack, and another question where you're going to have multiple multiple objects in the heap. I'll give you another one where there's multiple frames in the stack. So it'll look a lot like Wednesday's lecture. It's going to be two of the quiz questions. Here's a program with a bunch of objects going on the heap. Here's a program with a bunch of stacks going on, frames going on the stack. Tell me about the state of memory for both of those. So that'll be like the capstone of the quiz. Before that, I'll give you some code snippets and say, okay, we create these classes. What's this state variable? A little more toned down from the memory stuff on the first roughly half of the quiz. All right, any questions about this before we get into today's content? Let's do it. So this picture shouldn't make a ton of sense right now, but it'll make more sense by the end of lecture, at least we hope. So we have this class type hierarchy in Scala where classes are extending the state and behavior of other classes. We have this one main class. If you're familiar with Java, there's an object class that absolutely everything extends from. Everything is based on that object class. At least everything that's a class or object. In Scala, that type is any, because we're adding all the primitive values in Java into the type hierarchy as well. So everything extends any, and any has two different types that extend it. So in Scala, everything you have, unless it's any directly, which would be awkward to use, is either going to be one of these any vals or any ref. And anything that extends any val, we're going to put on the stack when we create a variable of that type. And anything that extends any ref is going to go on the heap when we instantiate it, and only a reference to that object is going to go on the stack. So if you have any question, any ambiguity about what goes on the stack or heap, this keeps it real simple. Any val, and this is everything that extends any val: double, float, long, int, short, byte, unit, boolean, and char, which mirror the primitive values in Java. These are all going to be compiled. All these any vals are going to be compiled down to primitives in Java. They're going to end up being on the stack. And when we pass these any values of any of these types, they're going to be passed by value. We're going to give the entire value, a copy of that value, to the calling method. For any ref, which is literally anything else, is going to go on the heap, and we're only going to work with references to those objects. The only thing that's a little awkward is strings. I should probably just not put strings on the quiz, but if you treat strings either on the stack or heap, I'll allow either one for any assessment that I give you. If you put the strings in either spot, it's going to be okay. Strings are a bit awkward. They go on the heap, but they're immutable and they just behave really differently. I talked about this a little bit on Wednesday. The references update as you use them, as you modify them. So you're never actually modifying that string on the heap, but you do get a new reference, and that kind of happens behind the scenes for us. Yeah.
In one of your previous examples, or what previous slide, I saw you assign a string value to like a class constructor, and that is stored in the stack.
Yeah. So in my examples, I put strings on the stack because in Scala, that's the way they behave. They behave as though they were on the stack. So if you stick with that, you'll be fine. If you do put them on the heap and then show that the references update, which would be more complex, it would be more accurate but more complex to write out. That'd be fine too. But if you just put them on the stack, I'm cool with that. They're technically not on the stack, but I'm okay with that. All right, so this is your overall answer to anything. What goes on the stack, what goes on the heap. With strings being a little ambiguous, but if we put them, pretend they're on the stack, we can keep it at that without getting too complicated for 116 anyway. You'll talk more about this in 220 and 250. The stack and heap, I mean. We will talk about the type hierarchy today, though. So we built this physics engine. We saw this jumper example. We want to say we're building a game at some point. That's pretty clear. I already gave you an example of the jumper game. But how do we do that? How do we start getting the functionality we want? So we saw an example of the platforms in the jumper game, and you can look at the wall examples too, and you can look at how the player is a dynamic object. But how are we doing that? So let's look at an example, something that we might not end up building this full game. But let's build a game that's going to have 3 objects in it. Hey, Drew. I was just wondering what you were doing. So we have players, of course, we know what that is. Health potions and balls that can be thrown. Health potions that'll restore your health. So just the simple basics of a game, just a few of the mechanics. I want to build this functionality and see how it would be built in a game. So we got these 3 objects we want to create. Let's see how we would pull something like this off. So let's review objects first. We have these 3 types, these 3 different objects that we want in our game. How are we going to make these happen? So for the player, there's a bit of information that I want to know about a player. It's location, dimensions, velocity, orientation. We don't have orientation in our physics engine, but I would like to know which way the player is facing so I can If I want to render their sprite different, even though they're still just a rectangular prism, if I want to render their sprite differently, or if it's a first-person view, I want to be able to know how that camera's facing so I know where they go. So we will want their orientation, even if it doesn't affect the physics. They have some health and max health, some strength, and they can use two different items, a ball or a health potion. Where the ball, they're going to throw it, and the health potion, they're going to increase their HP. And we would put all those state variables inside the object, and a couple methods that end up doing whatever we program them to do. We're going to create a ball in the same way. Maybe we want location, dimension, velocity, and also mass. Maybe we have balls of different mass, and if a player throws a ball, I'm thinking of a dodgeball game here. If a player throws a ball at another player and hits that player, it should do some amount of damage based on that mass, to see how much it's going to hurt that player. So if a player uses a ball, that use method that we deferred on the previous slide, I want to set this ball's velocity based on the player's orientation and the player's strength. So however strong this player is and however they're facing, that's where this ball should move. The ball should travel as a projectile in that direction. Health potion, when a player uses this, it adds to their HP, but not beyond their max. And we can have location, dimension, velocity as well. So a potion, for some reason, and a volume to figure out how much health it's going to restore. And this potion can have a velocity if these potions are flying through the air. You know, whatever we want to do in our game. We don't want to close any doors, so we're going to allow the potions to have a velocity, even if they're usually 0. So we have these three objects, but this is extremely restrictive. We can make a game with this. We can do this and make the game, and we'll probably get away with this player object, but we define ball and health potion as objects, which means we can only have one of them, one of each, in our entire game, which isn't going to make for a very interesting game. Most likely we want multiple balls, multiple health potions with different locations, different velocities, maybe different dimensions, different mass, different volume. We want to have some flexibility in our game, and we want to have more objects to interact with than just one, especially if we're thinking of a multiplayer game. If we do want multiple players too, and there's only one ball and one health potion, it's not going to make for a particularly interesting game. So we can do this, but it's not great, and this is why we use classes. We'll create player, ball, and health potion classes, and now we can create multiple objects of these types, storing their own instance variables or state variables, and have them in different states. So I can have two players in my game, each with their own location vector, and these players can actually be in different spots in the game world. That's something we probably want in our game. Same with balls and health potions. We can have a bunch of different balls with these same variables, but with different values set to these variables. It's probably what we want if we're making this game. So we use classes to do that. We create a class, and any values that we want to initialize, allow the caller to initialize through the constructor. Any values we want them to initialize, we'll put them in the constructor. So any of these values, when you create a new player, you would set their starting location, how large is this player, their initial velocity, orientation, max health and strength, and then health, another state variable that we don't allow the creator to control. It's just always going to be initialized to their max health. So we're going to put that outside of the constructor. Instead of having the caller set max health and initial health separately, we're going to always say you start at full health. We could also pull a few other of these out. If we always want the velocity and orientation to be 0, we do that too. Same with ball. We're going to change it to a class and put anything we want to let people initialize in the constructor instead of just hanging out inside the class. Initialize to the same value for every ball we create. And same thing with health potion. We're going to create a class instead of an object. Now we can use this class to create many objects of this type health potion. So if we want to use our ball class, we'll call this constructor a few times, create a few balls to add to our game world. They can have different velocities, different locations, different dimensions, different mass. And we're going to use this class to create multiple instances of this, create multiple objects on the heap, and then have references to them that we're going to use from the stack that our program is going to use. So we're going to have these references to these two balls, and when we edit either one of them, we're going to go to that spot in memory and then modify the values accordingly. So we're going to use these classes to create more objects. So far, that's reinforcing a concept we haven't really seen too much, but it is review from last week. We've seen objects and classes, but I want to reinforce how we would set this up if we weren't using inheritance. So now let's make a few observations about this. Well, this is going to get us where we want to go if we just use objects and classes this way. We're going to be able to create all kinds of different game objects and have them interact in our game. But one observation we can make is that ball and health potion have a lot in common. They both have a location, a velocity, dimensions, and something else that we'll come up with later. But they have, and a use method. Yeah, that's right. So 3 state variables are the same, and the name of the method that they have, the behavior that they have, is the same. So what we can do, I do have it right here. So, maybe we want to add more things. If we have mass and volume in either, which behave completely differently based on these two objects, but there might be something we want to derive from these values. What if we want to take the mass and volume and derive something for the momentum? We want to compute the momentum of potions and balls. We could compute that in either of these, and then we'd have some more common functionality between these two types. So what we'll do is create a third type named inanimate object, or whatever we want to call it. But for all the inanimate objects in our game, we'll factor out all of the common state and behavior and put them all in this inanimate object class. So location, dimensions, velocity all go into the inanimate object class, and the mass, which we can use to compute momentum, the mass and the use method both go in inanimate object. Then when we create our ball and health potion classes, what we'll do is, instead of writing these classes from scratch, starting at square one, what we're going to do is say that these classes extend inanimate object, which means they inherit, so there are two words, extend and inherit. They're going to inherit all of the state and behavior from inanimate object. So when I create a ball and say that extends this object, it'll inherit all of these, the state and behavior, and then I can add to that. Maybe I have this mass variable, which was not able to be factored out because health potion didn't have a mass. We're going to define that in ball and just add this one variable to all the functionality from inanimate object. Same with health potion. Volume couldn't be factored out because ball didn't have any mention of volume at all. So we'll define that in health potion only and add to it all of the state and behavior of an inanimate object. Yeah, question?
So if you wanted to access something in ball, like say you're creating a method that like changes the value, would you just use ball.location, or would you actually ball.inanimate.object.location?
So the question is, if I want to say access of the location of a ball, would I have to do ball.location or ball.inanimateObject.location? And the answer here kind of depends on how we set it up. It'll typically be just ball.location, even if it's coming from an inanimate object. But we do have to be careful in inanimate object to either declare that as a val or a var so we have access to it, or else we won't have access to it. So when we create an inanimate object, we can put all those state variables in the constructor, so they exist in to follow up on your answer here, I don't have val or var set on any of these, so they would not be accessible in the ball class, or outside of this inanimate object class at all. So I'm going to create an inanimate object, and I have these two methods that I create, but I have a pretty big problem here. the mass of an object, to compute the mass of an object, or what happens when I use this object, is going to be different for ball or health potion based on what they are. So what I'm going to do is nothing. I'm just not going to define these methods at all. What I'm going to do is declare the method headers. So I'm going to define, I have a method named object mass. It returns a double and takes no parameters. I have a method named use. It takes a player, returns nothing, returns unit. But I'm not defining these methods right here, which means I don't have a complete class. This class doesn't have everything defined. If I tried to create a new inanimate object and call its object mass method, what's it supposed to return? Well, it's undefined. There's no actual thing that it can return. So we actually can't create instances of this class because it's not fully defined. And when that's the case, we call this an abstract class. It's abstract, it can't actually exist. I can't just create a new inanimate object because it's not fully defined. This class only exists to store the common functionality of other classes. Once I have an inheriting class, we're going to call that a concrete class, as opposed to an abstract class. So when I create the ball class, I'm going to have a lot of my same functionality there. I still have my same constructor because that's how I want users to be able to create new instances of this class. But now I'm going to say extends inanimate object. So I grab all of this state and behavior, pass through my inputs to the inanimate object class, and here I have my vars and vals in the ball class, so I have access to these values outside of my class. And then call the inanimate object constructor. So some of this is Scala syntax, where if I extend something, I extend the name of that class and then call its constructor right inside my constructor that I'm creating now. So I'm just going to basically forward inputs from my constructor into the abstract class's constructor. Did I miss something? No. So we're calling that constructor because we have an obligation. We're creating a new inanimate object through the ball class. We do have an obligation to call that constructor to give inanimate object all the parameters that it's expecting, that it needs to be able to create an instance of it. Now here's where we define the actual behavior for those methods that we defined, that we declared earlier without defining. So we declared these objects, and we're extending an inanimate object, and we don't want this to be an abstract class. We actually want to create new instances of this class. We have to implement those methods. We have a contract, we have an obligation from the abstract class that we have to implement those methods. So let's do that here. And when we implement methods that have already been declared, we're going to use the override keyword. So we're overriding this behavior, which was no behavior at all. We're overriding that with some, still didn't update this slide. It's supposed to return the mass, but we're overriding it with some behavior specific to this class. Then we're going to override that use method with behavior that's specific to this class. So now, instead of having some use ball method, we're going to have a generic use method that every inanimate object has. Every inanimate object can be used by a player. And we do the same thing with the health potion class. We're going to set up the constructor in the same way, except we have volume instead of mass. And we're going to override the inanimate object. We're going to override those inanimate object it's bugging me. I got to fix my typo. We're going to override those inanimate object methods that we defined earlier. So we're going to override these methods. Object mass, we don't have any mass defined in the health potion, but but we're going to say that it's based on its volume. So we're going to say each unit of volume is 7 units of mass. So we're going to multiply whatever unit system we end up using. We're going to end up multiplying 7 there to be able to get our mass of a potion. And then when we use it, we're going to take that use potion method that we had earlier, and we're going to move it into this class with an override. Are there any questions at this point? So effectively what we've done is take 2 classes with similar state and behavior, factored out everything they have in common, put that in an abstract class, and then extended that class from both of the inheriting classes. So whenever we have common functionality, we're going to create a common type and extend that type. But why? Why do we do this? That seemed like a lot more work than just creating a ball and a health potion, and it ended up being more code anyway. Even inside our ball and health potion classes, there was more code than we originally had, so it's not like we really factored anything out. We didn't really gain much ground here. We just kind of convoluted things a bit. So why did we do this? One big thing is in inanimate object, all the extending classes are going to inherit all of that state and behavior. So if there's some behavior that we want to add to every single inanimate object, we're going to put that behavior in the inanimate object class. So if we want a new method to compute the momentum of an inanimate object, we can define this method inside the inanimate object class, call the object mass method, which is going to call, depending on whether it's a health potion or a ball, it's going to call whatever method is in that class. So if this happens to be a ball, and I call magnitude of momentum on a ball, it's going to call this object mass of a ball, which just returns its variable mass. If this happens to be a potion, it's going to call object mass defined in a potion, which is going to multiply its volume by 7 and return that value. So I'm calling a different method here depending on what concrete type I happen to be calling this on. And then I can share all of this code. Can compute the magnitude of this velocity, multiply the mass and velocity to get that momentum, the magnitude of momentum at least, not as a vector. I can get the magnitude of the momentum as a value, and now any health potion, any ball, I can just call dot magnitude of momentum and get that magnitude just with one method call, because both of those classes are borrowing this functionality from the inanimate object class. So anything I want to add to every single inanimate object, I throw it in this class, and now all of them have that behavior. As opposed to putting magnitude of momentum, the other way to do this before inheritance would be to cut and paste this method into health potion and the ball classes, and then instead of this dot object mass, replace that with the specific calculations for each one of those classes. That can be tedious, not the worst thing, but think about as you want to add new features to your game. What if I want a lot of more different types of inanimate objects in my game? I might want 100 different types. I might want vehicles and some weapons. I shouldn't have started listing things off. I don't have examples off the top of my head. But you can imagine a game that would have a bunch of different types of inanimate objects. I'm not going to create a whole brand new class for everyone. I'm just going to extend an inanimate object and give it the specific properties that that specific type of object needs to be able to behave, to be able to interact with my game. So this saves us a lot of time, saves us a lot of cut and pasting, saves us a lot of headaches, that we can just have all that common functionality here. But there's a much, I shouldn't say much bigger, but there's a big reason here to use inheritance beyond that. There's a lot of reasons to use inheritance. Most of us to keep our code clean and functional. But we're going to add this functionality to all of our subtypes. But something else we can do here is extend another class. We can build these inheritance trees, that what we call inheritance trees, where we have our ball and health potion inheriting and extending inanimate object, but we could have an inanimate object itself extend another class and have a chain of inheritances, or tree, since it can branch. And if we have our inanimate object extend dynamic object, which takes location and dimension, and set the dynamic object's velocity equal to our constructor argument, which we're going to do through the keyword super. So super is if we want to access the inheriting class. If I want to access something there, we'll use the keyword super as opposed to this. Because I have, I have a variable named velocity already, so if I say velocity equals velocity, it's just going to be a mess. It's not going to work. It's not going to do what I want it to. But if I do super.velocity, now I'm using the velocity in the dynamic object class, setting equal to this velocity. Yeah. And it'll look, if there's a whole chain of inheritance, it'll look for the next instance of a velocity variable of the whole chain of inheritance. So I'll extend dynamic object from inanimate object, and guess what? Everything that we did in physics engine is going to apply to our balls and health potions. They're going to behave just like dynamic objects, so as long as they have everything from our dynamic object, which is location, dimension, and velocity are the only things dynamic object needs, that's going to work with our physics engine. We create a world, we create balls and health potions, we throw them in the dynamic objects for that world, throw that world into our physics engine, and our game has physics now. And notice that we're never touching that physics engine code. Our physics engine, barring some extra features we want to add, that physics engine is done. We can plot that in any game we want to make with some physics, as long as all we're worried about is colliding with static objects and what face of the collision is, which you can do a lot with. If that's what we're concerned with, if that's what we need, which is all we need for this one, then actually we do need dynamic object collisions if we're playing a dodgeball game. Then we can not touch the physics engine again, but use all that code with our new types. So when we wrote physics engine, we had no idea that the ball and health potion classes would ever exist. But as long as ball and health potion somewhere in their inheritance tree extend dynamic object, they work with our physics engine. And our physics engine is going to update the physics of these new classes, these new types that we've just created, without touching the physics engine code, which is an important thing. We never want to update code that's written, it's tested, we know it works. We never want to touch that code again. So we want to make sure our code is easily extendable without modifying it. If we modify anything in physics engine to get this game to work, we got to retest physics engine. It's not something we want to do. It's a good way to introduce bugs into your games if you're updating existing code, existing tested code. It's easy to break code. So our inheritance tree here, health potion and ball extend inanimate object extends dynamic object. So ball and health potion are inanimate objects and they're dynamic objects. They inherit all of the behavior from both of these. And they fulfill all the contracts of both of these, so anything that works with dynamic objects or inanimate objects also works with our balls and health potions. And any other of the hundreds of different inanimate objects we might want in our game at some point, we're going to put them in this inheritance tree, extend an inanimate object, and it gets all that behavior, including working with our physics. So going back to this picture, any vales are on the stack, any ref on the heap. One of the most important parts of this chart is that your classes are always extending any ref. So any class or object that we create that wasn't part of Scala when we started, and in fact anything that's not one of these values, they're all going on the heap. Those are all going to be heap values, and we're only going to work with references to those objects. They're always going to be passed by reference. Only the reference is passed. Technically passed by value, but the value is a reference. So my health potion has 5 different types here. It's a health potion, it's a dynamic object, it's a physical object, it's a, that was supposed to say inanimate object. Inanimate object, it's an any ref and it's an any. It has 5 different types which, take it for whatever it's worth. It's 5 different types though. We'll talk about what this means, why we would use these 5 different types today. I foreshadowed a bit. It's mostly the example we'll see is so it works with our physics engine. Our physics engine works with dynamic objects. Well, Health Potion is a dynamic object, so it's going to work with our physics engine. It's going to be able to be updated with that physics engine. Which brings us back to the lecture.